So this is part 2. So now we have the results. By default it shows us the velocity here. If you notice in the results, it shows us the velocity, the slice plot. So in the title we see the slice plot and velocity magnitude. So in the settings for the velocity, this one here, we turn on these two checkboxes to show the units and the maximum and minimum values with the color bar. So we see that the maximum velocity is 1 meter per second and the minimum is 0, close to the wall as expected. And now if we click on the slice here, this shows us the settings for the slice plot, and it is showing us the YZ planes and 5 planes by default. So if we look at here, these planes are along the YZ, so in the YZ plane, and by default it's showing 5 plots. So we can just enter 1 and click plot, and it will show us the center plot here. If we notice here, this is along the center. So from inlet to outlet, you see that in the stenosed region you have the highest velocity with this kind of shape. Red color is the highest. Near the wall we have the lowest velocities, this dark blue color. And in the middle of the region we have comparatively higher velocities, and these are actually parabolic profiles, which we'll see later. So this is the kind of one view of the contour plot or slice plot. So it gives us one view for the velocity. Next we want to see the vector plot of velocities, which will show us the magnitude and direction both. So in this velocity here, we click on the arrow volume, this one, and this shows us the 3 velocity components, u, v, w along x, y, z. So we click on the plot. So in the title we see that currently it is showing 2 plots at the same time, the slice and the arrow volume. So for better visualization of the arrow plot, we can just disable the slice. So right click here and click disable. So this is dim and disabled. We have the arrow plot here. So we again see that the stenosed region has the highest velocities because the size or length of the arrows are proportional to the magnitude of the velocity. So these are bigger arrows, so larger velocities. And these are comparatively smaller. And this is the default 3D view. So if we select the YZ view, with this being the inlet and this is the outlet, and the length from 0 to 100. If we zoom in a little bit here, by holding down the wheel and then moving the mouse. So if we imagine a line connecting this arrowheads here, you can see the shape of a parabola. So that is the parabolic profile. Okay. Next we want to add a streamline plot. So again from this velocity bar here, we click on the streamline, and for this we need to specify a face or boundary from which the streamlines start. That goes in this box here by selecting the face manually. So we select this inlet face or inlet boundary here. So we see that now 1 coming in here, and we change this to tube. Tube looks better. And click the plot. So we see these red tubes showing how the fluid is flowing from the inlet to the outlet. And if we also want these tubes to represent the velocity magnitudes, then we right click on the streamline here and click color expression. And in the setting for this one, this expression field here, this shows the variable we are going to plot. So currently it is SPF, that is for single phase flow, dot uppercase U means velocity magnitude. So if we click this, we get the velocity magnitudes here. So we see that again lowest velocity near the wall and higher near the center, and we see that near the stenosed region we have the highest velocity with this red yellow color. And if we carefully notice, we see that after it passes through this region, there is this region where is no fluid flowing. So this is because of some change in pressure or pressure loss or something, we'll see later. So this is the empty space created here. Next we want to plot the velocity, shear stress profile and pressure variation from inlet to outlet. For that we'll create radial lines at 3 position and 1 line from inlet to outlet, and we will choose the center position. So for that we click on here results, and we select cut line 3D, or alternatively we can right click on the data set and get the same options like this. So we select cut line 3D, and for easier understanding, or you can just label this. This is kind of naming this as radius at 20. Say we're taking at 20 millimeters, so we name like this. And for positioning it, so our circle is at ZX plane, so we click on the ZX. So to define one line we need two endpoints. So one endpoint would be at the center, so it will have a x value of 0 and z value of 0, and if we take the other line at here, so it will have a z value of 2.5, which is our radius, and x value of 0 still. So we write x equals to 0, z equals to 2.5, because the 2.5 is radius here. You will use the radius of your cylinder, and we want at 20 millimeters length, so we write 20 here. If we click plot, and we already see the red line there, and in the 3D view, so we have the radial line at length 20 millimeter, and it is here, radius at 20. So we want two more radial lines, one at 80 and one at here 50 near the stenosed region. So we can just duplicate this, right click and duplicate, and for this one the label just change this to 80, and this one everything remains the same except that it is at 80 millimeters, so we just change this to 80. And if we click plot, we see the line at 80, and we can duplicate this line again and change the label here to 50, and change this y values to 50, because y is along the length. And if we notice carefully here, at 50 millimeters near the stenosis, the radius is not 2.5 anymore because it is decreasing, so it should be 1.25, because this circle has a radius of 1.25, so 2.5 minus 1.25 gives us 1.25, so this would be 1.25. So we have this radial line here. So we have our three radial lines there, and we'll draw one more line going from the inlet to the outlet, and in the center, so we do this one. Can name is at the axial line, and this would be starting from x equals to 0 and z equals to 0. So this would be 0, and it is along throughout the whole length, so starting from y equals to 0 up to 100. So 100, and if we click plot, we see this line starting from x zx plane 0 0 up to all the way up to y equals to 100. So this is the axial line. So now for making the velocity profile, we select this one, the 1D plot group here, and then we select line graph. This will make an XY plot, so we select this one, and we want the x-axis of the independent variable to be the radius, so we select the radius from here, the one we made now. So radius at 20, and it shows us that the y-axis data would be the velocity magnitudes. That is what we want. Units are correct, so we click plot. That is our plot. Velocity magnitude on the y-axis and the radius along the x-axis, and arc length is the default name for any distance variable in the COMSOL. So we add the two other locations. So for that we click the line graph again, and now we select the second radial line at 80 for the x-axis, and we click plot. The second line is added, the green line, and next we add one more line graph so that we have all of them in the same graph, and We select the line at radius 50. This is at the stenosed location. Click plot. So we see this is different. So we now place correct or nice axis labels, titles, legends, etc. So for that we want to identify which line is at which location. So we, on the line graph 3 selected, we click on the legends here, we click on the show legends and legends manual. Since this is number 3 is at 50, so we write 50 millimeters here. So it's shown there, and similarly we do the line graph 2. Turn on this show legends. To manual this is 80, so we write it at 80 millimeters. And then we click the first one and do the same thing. This is 20. And then we click on the 1D plot group here. Since we added 3 lines, so this line graph text is showing 3 times. So we click on the title, select manual, and replace this whole text by writing velocity profile. And this arc length, this is the X label, so we can just edit them here. So if we turn on this checkbox, so we can just write the radial position, so we have the radial position and velocity. So this is our velocity profile, and we can see that near the center, this is radial position 0, we have the highest velocity. Near the inlet and outlet, that is 20 and 80, but this is only 0.35 meters per second. But at 50 mm near the stenosed location, we have higher velocity, that is close to the 1, so almost 3 times larger. And this one ends at 1.25 because the radius ends at 1.25 there. So for the shear stress profile, we can copy this whole plot. We'll just replace the variable there. So we right click and duplicate this. So this is copied there. And if we come back here again, so we can just flip this axis here and click the plot so that we have the radius along the vertical direction and velocity along the horizontal. This is kind of similar to the view we see in our textbooks. Like this would be the top half of the tube, so the velocity vectors are along this direction. So you see that in the stenosed region the velocity vectors are, the velocity magnitudes are larger, right? This vector's length is larger. So this is, and this is the top half, so this is symmetric about this axis. So this gives us the parabolic profile, something like this. So now if we go to the second one, and for the shear stress we have to modify this expression. So these variables are available here in the replace expression. So if we click the cursor here and click here, and under component 1, our geometry and everything is under component 1 here. Under component 1 we have these variables. So in the laminar flow, velocity and pressure, these are the variables, velocity and pressure. We see the shear rate is there, SPF.SR, and this is the pressure, this is the velocity magnitude, these are the individual velocity components, U, V and W, and the properties are here. So you have the viscosity and density here. So you can just right click, double click and select them here, or you can just type them in directly. So you can just type SPF.mu for the viscosity and SPF.SR for the shear rate. That is the product. That product gives us the shear stress. and currently this unit is for the velocity, but when we enter this and click, it is automatically changing it to the correct unit for shear stress, Pascal. So if we click the plot, so it has changed for one location, so we can just copy this expression here and paste it for the other two. And click plot. So now we see that this is the plot of the shear stress. So at the center, which is radial position is 0, the shear stress is 0 or very small, as it should be, and shear stress is highest near the wall. So for the locations 20 and 80, shear stress increases to values of something like 2 Pascal near the wall, but at the stenosed location it increases up to 24, so there is a big increase in shear stress. And we should just change the title here, so click on here and change this to the shear stress profile. And change this one to shear stress. So you have this shear stress along the y and the radial position along the x. And the last thing, we want to plot the pressure along the length. So we click on, we go to the results, 1D plot group, and again line graph. And this time our length would be the line along the length of the tube. So we select this axial line. And we want pressure, so pressure you can just check again here, it's just a lowercase p, it's case sensitive, so lowercase p, you can just double click from here or enter the lowercase p, so the unit is changed to Pascals. We click plot, you see that from the inlet where we specified the 5000 Pascals and outlet we specified 4500, so it decreases like this. So this linear decrease is in the portion where the radius was constant, then there is sudden decrease in radius at the start of the stenosis, so this pressure drop is due to this. Then the radius is increasing with the 2.5 millimeter value again, so there is the increase of this pressure. And then after in the downstream portion where radius is constant again, there is again the linear decrease of pressure. So we can just change this one to again radial position, and so this will show us the pressure variation from inlet to outlet. So just change this to so yeah, so we have all of them, so this is the end.